I am Laszlo Frazer from the ARC Center of Excellence in Exciton Science at Monash University. This video is being recorded during the coronavirus pandemic for the purpose of making it easier to do upconversion research from home. So we are providing a free simulation package for modeling the performance of photochemical upconversion, also known as triplet-triplet annihilation upconversion or triplet fusion. This package will be useful to you if you want to predict the performance of photovoltaic devices which are augmented by triplet fusion. You may use this software free of charge. We do ask that you cite our paper in any scholarly outputs you have, such as journal articles. If you have any results that are not published, then we do appreciate it if you email us and let us know about them because we are curious. This software is available for use with Windows, Mac, and Linux. This video will focus on the use of the software with Windows. If you use Windows, you have the advantage of a convenient graphical user interface. If you are going to use Linux or Mac operating systems, then you will need to be familiar with the use of a command line interface and a compiler. Assuming you're using Windows, you need to download two different packages. The first one is called Zenity, which is not provided by us. Zenity is a very convenient way to make an easy user interface. Once you've installed Zenity, you need to extract the upconversion simulation package version 1.0, which is downloadable from our website. And you will find a folder which is full of various files. This includes the manual for the software. I recommend you start out by performing the example calculation, which is given in the manual. The first step is to run the upconversion.exe shortcut. This will start the program. When you're using this program, there are going to be two parts to that. One is going to be numbers that you input, and the other is going to be files that you input. We're going to start out with the numbers. The first number you input is the simulation depth bins. This is a critical value, which is somewhat confusing. Simulation depth bins controls both the systematic and the random error of your calculation. If you want to create a high quality calculation, we recommend that you use at least 100,000 depth bins. If you just want to run the simulation quickly to see if it works, then we recommend you select 100 depth bins. This will introduce a lot of error into your calculation, but will be quick. If your device is poorly designed, then you may need to increase the number of simulation depth bins used to be bigger than 100,000 in order to get accurate results. If you're not sure you've selected the correct number of depth bins, try increasing it by a factor of 10. If the result of your simulation does not change very much, then you're fine. The next parameter to consider is the depth of the anabathma. For typical laboratory experiments, that's going to be the thickness of the cuvette, which contains your sensitizer and emitter that's performing the upconversion. In an efficient device, you will typically find that the depth is much smaller. The units of depth is centimeters. The next parameter to consider is the triplet exciton decay rate. All the rate constants in the simulation are based on this differential equation, which is the rate of change in the number of excited states per unit volume is equal to an excitation rate minus K1 times the number of excitations per unit volume, where K1 is the triplet exciton decay rate, and then minus the annihilation rate constant times the square of the number of excitations per unit volume. The triplet decay rate, K1, is in units of per second. Typically this value is around 1,000 per second, but it will depend on the content of your device. In many cases, the amount of oxygen in your device will be the most important factor. The next rate constant, the triplet annihilation rate, K2, describes the efficiency with which triplet excitons that are near each other, or triplet excited states in different molecules that are near each other, destroy each other. So, the larger this constant, the more upconversion you get. People use different units for this quantity. Our software uses centimeters cubed per second. When you're adjusting this value, you should keep in mind that it's very easy to introduce a lot of systematic error in this value by relying on experimental results. It's quite difficult to measure this rate constant, and very often those measurements have not been reproducible from lab to lab. So your choice of K2 is likely to be the largest source of systematic error in your calculation. The next parameter is the yield eta. In some emitter molecules, when you annihilate two triplet excited states, you always get a singlet excited state as a result, and that singlet excited state emits fluorescence. If your system behaves that way, then the yield eta is 1. In some emitter molecules, annihilation doesn't always result in that singlet excited state, which is fluorescent. In that case, the yield eta is a smaller fraction. Eta should always be between 0 and 1, where bigger is better. The next parameter is the sensitizer concentration, which is in units of moles per liter. The larger the sensitizer concentration, the more efficient your device will be, if everything else is kept equal. The emitter concentration is also in moles per liter. If you select a value that is unreasonably low, then the number of excited states will exceed the number of emitter molecules, which does not make sense. We do not check to see if that happens. Next is the solar concentration. The solar concentration is a measure of how brightly your device is illuminated. That would be the illumination before a solar cell and before the first interface of the device. The units of solar concentration is suns, which is equal to 1 kilowatt per square meter. This is designed with the assumption that your illumination spectrum is the same as the AM 1.5G standard for solar spectral irradiance. You can change that later on. If you do so, you need to very carefully consider what solar concentration means. So if you use a monochromatic light source and you input the spectrum of a monochromatic light source into the simulation, then the units are now 1 kilowatt per square meter, and that is no longer equal to 1 sun. So the units of suns assumes that you're using the standard solar spectrum. The next parameter is the band gap of your solar cell. This band gap determines which light is captured by the solar cell and which light passes through the solar cell and reaches your sensitizer, like you want it to. The band gap has units of nanometers. Next is the solar cell absorption parameter. If you are using thin film solar cells, then we recommend that you read the paper Evaluation of the Talk Method for Optical Absorption Edge Determination from the Burney group that is cited in the manual. If you're using a thick solar cell, then we recommend you use a very large value for this parameter. We suggest 1 billion. Note that we can only simulate the absorption spectrum of direct band gap solar cells. The second to last parameter is the difference in triplet energy levels in electron volts. This is the triplet energy level of the sensitizer minus the triplet energy level of the emitter. If you do not know the value of these energy levels, then we recommend you assume that the difference between the energy levels is big enough that all of the energy transfer from the sensitizer to the emitter is strongly exothermic, and therefore the equilibrium of excited states will all be located in the emitter molecule. If your system that you're simulating is reasonably well designed, this will be the case. So what we're recommending is, if you don't know, assume it's a 1 electron volt. That will work pretty well. Finally, you should enter the temperature of your device. This is really only relevant if the difference in triplet energy levels is not so big. The units of temperature are Kelvin. Most people operate their experiments at 300 Kelvin. However, solar cells in the field can operate at a higher temperature. After you have clicked OK to submit your upconversion simulation configuration values, you will now need to select 4 different files. You'll be prompted to pick each file, and the software will automatically copy that file into the directory where your program is located. So that will overwrite files that are already there. The 4 files that you will need to copy will be the sensitizer absorption spectrum, the emitter absorption spectrum, the emitter emission spectrum, and the illumination spectrum. The first one will be the sensitizer absorption spectrum, absorption.txt. This is the sort of data that you would measure using a UV-Vis. When you measure your absorption data, there are some important considerations. So you need to make sure that the baseline is properly subtracted. You should make sure that the values of the absorption spectrum are not negative, that the maximum values are not saturated in your detector, and that the units of your absorption spectrum are per molar per centimeter, or in other words, liters per mole per centimeter. In your data file, the first row gives the number of rows of data. The software is not smart enough to figure that out on its own. You need to tell it. From then on, the first column is the wavelength of the measurement, and the second column is the molar absorptivity. Go ahead and try it with the example file we've provided. The sensitizer absorption spectrum is of critical importance because it determines how much light is captured by your device, which limits how much light can be converted to useful work. The next file is the emitter absorption file, and it has the same format as the sensitizer absorption file. The name of this file is emitter_absorption.txt. Emitter absorption is important to self-absorption. That's when the emitter fluorescence is reabsorbed by emitter molecules. This is simulated in our software. The next 2 files are the emitter emission and the illumination files. These 2 files use the same format. The emitter emission file is the sort of thing you would measure with a fluorimeter. So what you'd probably do is take your emitter molecule, dilute it to a low concentration, so there's not very much absorption, and measure the fluorescence spectrum with a fluorimeter. The type of file output you get from the fluorimeter is not correct for use with this simulation software. You need to transform it in the same way the illumination file is transformed. The illumination spectrum is the spectrum of the light that is incident on your device before it reaches the solar cell. In the example we provide, we're using the standard AM1.5G solar spectrum, assuming that you would want to use your device somewhere on the ground to collect sunlight and produce electricity. The file format is as follows. The first row of the file gives the number of rows of data in the rest of the file. Then there are 2 columns. The first column is a probability, which must be from 0 to 1. The second column is a wavelength in nanometers. The probability gives you a cumulative distribution function. This is a bit confusing. Light spectra are usually presented as brightness as a function of wavelength, as in the purple curve. We use cumulative distribution functions instead. The cumulative distribution function is like the integral of the fluorescence spectrum or irradiance spectrum of the sun. This graph is an example using the solar irradiance. So the purple curve is the brightness of the sun per unit wavelength per unit area. The cumulative probability is the integral of that, but it's changed so that it starts at 0. So at the smallest wavelength, the cumulative probability is 0, and at the largest wavelength, the cumulative probability is 1. The probability distribution must be increasing as a function of wavelength. You'll notice that it increases faster around 500 nanometers, where the sun is brighter, and it does not increase at all in areas where the brightness of the sun is 0. If you are simulating a monochromatic light source, you need to make your cumulative distribution function smooth. The reason for this is that it will be interpolated by the software, and if it's not smooth, then we don't know what will happen. Most people will do fine by assuming the ordinary standard solar spectrum, which is the file we've provided. It's much more likely that you will want to customize your emitter emission spectrum according to your choice of emitter molecule. The range of wavelengths in the emitter emission file must be within the ranges of the wavelengths in the absorption spectra. Your emitter emission file will be automatically renamed to emission.txt. Your illumination file will be automatically copied to spectrum.txt. Once you have selected all your files, your calculation will begin. You will get a pop-up message which tells you when the calculation started. After some time, you will get another pop-up message which shows you the result. The first number in the result is the figure of merit of your fusion system. That is a current per unit area. The other numbers that you will see are just a repeat of the input that you gave at the start. The units of the figure of merit are milliamps per square centimeter, and in the example, that's 5.7 times 10 to the minus 2 milliamps per square centimeter. To interpret the figure of merit, you need to know that it interprets each photon, which reaches the solar cell, as becoming 1 electron in your current. The electrons which are generated by direct illumination of the solar cell are not counted. Only the electrons that are generated by upconversion contribute to the figure of merit. The efficiency of the solar cell at converting the upconverted light into electricity is not considered. You also do not consider the voltage of the solar cell, which is an important factor in energy efficiency. Using the upconversion figure of merit calculated by the software, you can calculate the total power output of your device. First, you need to take the figure of merit and multiply it by the external quantum efficiency at the wavelength of the fluorescence. This is not the same as the external quantum efficiency of sunlight because it has a different spectrum. Also, it's on the back side of your device, not the front side of your device. The efficiency of the two sides could be very different. Once you've done that, you now need to add all other sources of current per unit area. So that would be the current generated by the sun shining on your device. When you found the total current, you now need to multiply by the voltage of the solar cell. This will give you the total power output of the device in watts per unit area. We hope this information was helpful to you and that our software is useful to you in your efforts to improve clean energy technology. If you have any questions, please send me an email at any time. Thank you.